Hello, everyone, and welcome to another exciting episode of Music on the Brain. My name is Ryan Maloney. I work in the Programming and Education Department at the National Jazz Museum in Harlem. We're excited to have you guys here today. If you've been to one of our sessions in the past, you'll know that it's a really fun way to learn about music and the brain and everything in between. This is presented in partnership with our friends at the Zuckerman Institute over at Columbia University. And for those of you who are new to the National Jazz Museum in Harlem, we're located on 129th Street, just off of Lenox Avenue in Harlem. We are not open to the public currently, but you can check out our programming calendar on our website, jmih.org. You can also sign up for our newsletter, and if you like what you see and experience, you can always donate to the museum right through our website, or you can text the number 41444. Text the word jazz to the number 41444, and that'll help you facilitate a donation as well. Really appreciate you guys all for joining us today. We already have a good group on both our Facebook and our YouTube. Feel free to share. If you take a minute and just click the share button, let some of your friends and enemies know what's going on, and they can join us, and it really helps us to spread the word. So please go ahead and click share. I want to introduce our host for the day. Helen Sung is one of the outstanding piano players on the planet, and has been making beautiful music for a long time, and has traveled the world sharing her gift. One of the things that makes Helen so incredible is not only her musicianship, um, but her kindness and her inquisitiveness, which kind of led us down this path of exploring the relationship between music and the brain. Helen was the inaugural jazz musician in residence at the Zuckerman, and and it has continued beyond that initial uh, relationship between Helen and the Zuckerman. We have continued to explore opportunities to learn more about this incredible and beautiful interaction between music and the brain. So I'm going to bring Helen in here. And Helen, I just want to say welcome and thank you for joining us.
Thank you, Ryan. It's always so great to partner with the National Jazz Museum in Harlem, and thank you for the hospitality.
Of
And
course.
I'm really excited about today's topic. It's something very close to us musicians, as you know, the subject of hearing.
Sure.
How we hear what we hear. So, if y'all will indulge me, let me start with some music, and we'll get the party started. So thank you again for those of who are just joining us. My name is Helen Sung, and I want to welcome you to our latest installment of Music on the Brain, a program done in partnership between the Jazz Museum in Harlem and the Zuckerman Institute. And the pieces I just played, the first one is by the great Marian McPartland. It was the theme song for her long-running NPR jazz show called Piano Jazz, and it's called Kaleidoscope, followed by a great standard called I Hear a Rhapsody. And I like that tune, but I did kind of choose it because of the title, I Hear a Rhapsody. And today we are talking about hearing and listening and what that means, sound, how does it become something that means something? And I was reading an article that I thought said something really profound. They said, when we talk about listening, hearing, we immediately think of our ears. And that is true. We need our ears, but it's our brains that help us process what we hear to make what might be technically called a jumble of noise into something that is coherent, that we understand, and that has meaning. So I'm so excited to welcome our wonderful guest scientist today. We have to give her an extra shout out because she is beaming in all the way from India. So she's staying up late. So we want to thank the wonderful Prachi Patel and welcome her. And I want to introduce you to her, let her share a bit of her story, how she came to study neuroscience in her area of research. So welcome, Prachi.
Thank you so much for having me here today, Helen.
My pleasure.
So originally I'm from the western part of India. The state's name is Gujarat. It's famous for agriculture. We export a lot of food to the entire India. And since I was little, I really loved science. It felt like magic to me. And when I had to pick a discipline, what better than the human brain, because it really controls your entire body and it evolves over years. Because, for example, if you look at your brain, Helen, versus mine, there will be striking dissimilarities because you're a musician. You have so much practice. So especially the regions of your brain that process music will be highly specialized.
Wow.
So, yeah, that's how I got into science. And I've been with Columbia 6 years now, exploring the human brain.
Amazing. Thank you. Well, I would love for you to tell us how do we hear? What are the physical structures involved, and how does it work in the brain? So please take it away.
I'd love to. So here you guys can see that we have an ear as well as the human brain over here. The sound enters the ear and it goes through this squiggly thing in blue over here called cochlea, which breaks down the sound into frequencies, and these are fed to the brain all the way on the top in the area in pink over here, which is the auditory cortex, which processes all the sounds that we hear.
Can I ask a quick question?
Mm-hmm.
What is the purple on the right? Is it the same thing? Is it just
That's the same
left and
thing.
right? Okay, cool. So I want to hear more. I like scientific terms like squiggly. Can you tell us a little bit about what that sounds very intriguing.
Definitely. So the squiggly thing over here, we have it in this slide as well. And you can see the colors that go from purple all the way to yellow. So that's really the sound being broken apart into its frequency contents. So whatever we hear, whether it is music, speech, any kind of noise, it's first broken down into its frequency contents at this part of the ear called cochlea, the squiggly thing. And it's almost like a piano. It goes from low to high frequencies. And this map that is generated in your ear travels all the way to your auditory cortex over here. So you can see the same map from purple to yellow on your brain as well.
Amazing. Yeah. When I was jazz artist in residence at the Zuckerman, I remember scientists saying exactly what you said, like the cochlea, if you unfurled it into just, it's squiggly because I guess there's not enough room to have it pulled out straight. That left to right, like a keyboard, the lower frequencies on the left, ascending all the way to the higher frequencies on the right, and that the cochlea have these tiny, they're not technically hairs, right? But they look like hairs. Is that why they call them hairs? Or?
Exactly. They're called hair cells, and their job is to convert the frequencies into electricity. So the map still is intact. It's just in form of electricity now, which is fed to the brain.
Amazing. Well, can I ask another question?
Mm-hmm.
So I was I was driving over the weekend and I was listening to they have like this TED talk for an hour on NPR, and they just happened to be talking about silence and sound, and how sound sound waves need a medium to move through. That's why technically, since there's no atmosphere in outer space, sound can't travel. Is that true? But like we have different gases in the air, and that our ears have been evolved to be able to, because it pushes, because can you, I mean, my question is probably not very clear, but it's pushing something, right? Something's being moved around to activate the hairs.
No, that is a very good question, actually. So light does not need a medium to travel. That's why we can see sun's light, but we cannot hear the sun because
Oh,
the
right.
sound doesn't reach Earth because there's no medium there. So the sound does need a medium to travel. And initially, the medium is really the air pressure. And the air pressure beats your eardrum, and that pressure beats the liquid inside the eardrum. And that liquid changes like that kind of vibrates the cochlea, and that's where the frequencies are being processed. We have a video for that as well.
Amazing.
Yeah,
Oh my God. Okay, well, I'm excited about this
there you
video
go.
here.
There we go. We do have this video. So you'll see how the sound goes from the ear. The first thing you'll see is the eardrum beating by the sound pressure. And this is the cochlea. And that pressure is converted into waves over here on cochlea, where the frequencies are being broken down.
Amazing. Amazing. So that kind of was the way the cochlea unfolded. It's like if the piano player or organ player was looking at us. So kind of a mirror image of low to high.
Exactly.
Very good. I'm just a little picky that way since I play the keyboard. Lovely. Oh my God. Well, okay, so we hear sound, and then our brain enables us to make meaning of what we hear. So I think a lot about, different ways humans communicate, and one way is through the written word, like in our modern world, texting and email. But when we actually convert those or express those written words through sound, through the human voice, which some people call our original instrument, it conveys a lot more meaning through tone, through how we say it, the timbre of our voice. So maybe this might be a good time to ask our listening audience, because in our modern world of online dating, I've gotten advice like, well, if you're in an argument with your boyfriend or girlfriend, it's better to talk on the phone, don't text about it. So are there some things that you would personally rather have somebody say to you versus to read? Are there some things y'all can think of and want to share with us? Maybe I'll ask you, Prachi, first. What are some things you like to actually have someone say to you rather than written out?
Any kind of happy news is definitely better conveyed over voice
Yes.
as opposed to a text.
Yes. And also maybe for me, if somebody wants to borrow money from me, I'm joking. Any takers, any brave souls? Okay. Well, I think one thing that we can all relate to is the very famous, when somebody expresses love, I love you. I think it's much nicer to hear it said. rather than, and a text is nice too, especially if you have a lot of emojis, I suppose. But it's nice to, apologies. Thank you, Sunny. Yeah, that's a good one. Apologies, I think, mean a lot more when we say it through our voice. Wonderful. Well, I know a big part of your research is how the brain makes meaning of what we hear, and I would love to hear about you do an experiment about how we can differentiate between speakers and, how we understand. So I would love to hear more about that.
Well, this is an example of a pre-COVID era where we could go to restaurants, for instance, and be in a crowd. So whenever usually you're in a restaurant and you're having a conversation with someone you went with, there's always some noise in the background going on. There are multiple people talking in the background. Yet you can very effortlessly focus on your conversation. And my research focuses on how your brain can amplify the voice you're interested in and shut down everything in the background. So we can probably go to the next slide where we have a small demo. All right, so here you'll listen to a male and a female talker simultaneously talking. And the listener, is asked to focus on the male talker. And just by using their brain signals, we could figure out that it was the male in the mixture that the person was listening to and not the female. And we could use this information to help people with hearing deficits to amplify the person that was attended to in the conversation. You can probably try playing the demo.
How to be a shepherd. Dogs are great companions for a variety of people.
Especially when you know how to do it.
Have you ever thought about having your own
Shepherds
companion?
can be found all over the world.
If you do not have a dog.
So this is where the person started focusing on the male voice, and you'll see what happens next.
Oops.
How to
take
be
care
a
of
shepherd.
dog. Dogs are great
Being a shepherd can be a
companions
lot
for a
of fun,
variety of people.
especially when you know how
Have
to
you
do
ever
it.
thought about having your own
Shepherds
companion?
can be found all
if
over
you
the
do
world.
not have a dog yet,
Any
you
place
need to
from the
understand
desert
the
of
difference
Israel
between
to
breeds
the
before
highlands
making a
of
choice.
Scotland.
The breed of a
Find a good
dog
place
can
to
have
live.
significant impact on its
Many shepherds
personality.
like to live
So
in
this is what
Size,
happens in your brain.
If you want
health,
to do this,
If you
and
switch
required
attention to the female,
For example,
you'll see what happens.
long-haired
want to
breeds
live in the United
like
States,
collies
move
may
to
be
Idaho
needed,
or
but they
Wyoming.
require frequent
Buy
brushing.
a sheepdog.
If you do not have time
Some
to devote
sheepdogs
to
are better
weekly
than
or
others.
even daily maintenance,
You would do
you
best
may
to
need
look on a
choose
dog
different
market
breed.
online or see
The
if you can
American
find a breeder.
Eskimo is bright.
That's amazing. So it's like your brain actually makes the sound louder in your brain or in the auditory cortex, like you said earlier. And that is what this experiment shows. If they focus on the other speaker, the brain amplifies the volume in your mind.
Exactly, that's what happens in the brain.
That blows my mind away. So does that mean the electrical signals get stronger? Is that what it means? Okay.
So earlier we saw that map from purple to yellow of the frequencies in your brain.
Yes.
So overall, any kind of speaker will have some kind of information about their pitch. So if you're listening to the male talker in that piano, the male pitch will be highlighted. So that's how the male voice is amplified in the brain.
Wow.
And when you switch your attention to the female pitch gets highlighted in the map on your brain.
I admire how you guys come up with experiments, and it must be exciting to get results that back up your hypotheses. That's amazing. Yeah, so as I talked about, text versus hearing the words spoken to you, we have that analogy in music. We have musical scores. Like here's one of my favorite standards, Willow, for me. We can look at that, and as a musician, I can kind of imagine in my mind what it sounds like. But if you actually play the song, and oftentimes when different musicians play the same song using the same chart, it can sound very different. So I'm going to do something fun. I'm going to play a few versions of Willow Weep in Me, and as you all listen, really pay attention to what feelings you might be feeling or what kind of responses you might be having to the sound, and just revel in the fact that, you know, we all are using our ears, our cochleas, eardrums, cochleas, and then into our auditory cortex, and then our brains. I think it's so cool. All right, here we go. Okay, now what if I played Willow Weep for Me on this instrument, which is called a melodica? Think about how it strikes you, any different kind of response. Anybody want to share their thoughts? I love the question that Ryan put up. Any differences that you notice between the sound of the piano, the sound of the melodica, the different ways, the two different arrangements I played of Willow Weep for Me? Tinny, it's as if I can hear my... Yes, yeah, the melodica definitely is a different type of instrument. To me, it reminds me of the accordion, and definitely has a more reedy sound, a little more piercing, more discordant. Cool. That's part of what we call timbre, the tone, the characteristics of a sound. Great. Well, melancholy. Okay. Yeah. Any thoughts about the two different ways we played? I relate far more to the sounds of the piano, but more distinctive and rich notes. Thank you. Well, we're a little bit handicapped on the melodica because it's just one type of sound, it's not electronic in the true sense, but the piano is much bigger too. Okay, I love that. More limited in its emotional range. So let's expand on that idea a little bit, because timbre, tone, characteristics of sound. Let's do a little experiment. I'm going to welcome Prachi and Ryan to the screen, and we're going to each say a sentence that will just highlight how a timbre, based on who we are, our vocal cords, can make this sentence very different from one person to the next. So I'll go first since I'm making y'all do this, okay? So, and then we'll go to Ryan and then Prachi. Okay.
And we're listening for the differences between our voices?
Difference in timbre and if the way how that might evoke a different response. So let's hear it for the brain. So Ryan?
Let's hear it for the brain.
Let's hear it for the brain.
Nice. I vote for Prachi. I like her voice. But just three of us, we said the exact same words, but a little different from one person to the next. And that brings us to the next major piece of Prachi's research, where you did experiments based on how does the brain hear the same kind of sound or melody, but with different instruments, and is there differentiation, like you differentiate between different speakers in a busy restaurant, between instruments?
Definitely, let's do that. So we talked about that frequency map on your brain, which basically highlights what sound frequencies you're hearing. But what if you play the same note with multiple different instruments? So if you play the same note with piano versus violin, for instance, it's still the same frequency, but you can perceptually tell the difference between these two instruments. So my research focuses on how we can tell them apart. So first, when you look at the ear, this is what really happens in your ear. Each color over here is the instrument group, and you can see how the similar colors have clustered together. So even though these different colors are playing the same melody, they're being torn apart and clustered together because they are sort of from a similar instrument family. So you can see a pattern emerge over here from purple to green to red to blue. And look at what happens in the brain. Can we have, yeah, there you go. So you still have the same pattern show up where the pattern goes from purple to green to orange to blue, where each color is a different type of instruments. And you can see how the instrument map goes from ear to the brain as well.
That's fascinating to me because if it's playing the same note, technically it's the same frequency.
Exactly.
But sound timbre must have, I need to research this more, but I imagine it has, one instrument sounds different from the next based on how the sound is produced and overtones. So that must be where the difference is, and the brain somehow knows that, even though the same frequency is being generated in the cochlea. Is that true, or what are some of the other differences that might be happening?
That is exactly it. It's still the same frequency, but the way the frequency works, like how fast the frequency dies down, depends on what instrument you're using.
True.
So those differences are captured by your brain as well.
That's so amazing. Well, let's talk a little bit about just the common experience of hearing. I wonder if there are sounds, and we evolved this way to hear this way, that some sounds we universally find people respond the same way, like a baby crying, or when you're laughing, ha ha ha, that we know that means something good, or when someone screams. Is that true? Or maybe let's listen to some examples in music, and as you listen, we encourage you to tap your responses in to what you're hearing. Right. Nice. Thank you. I saw some really great responses. This is music from iconic films and from sporting events. Mixed apprehensive with humor. I like that. Power, yes. Yes, the first example, I think y'all all know Jaws. I remember being terrified when I saw that movie. Bombastic. Yeah, the last one, that is the theme from the Olympics by John Williams. The grandeur, yes, proud. That's really good. The second one was from Mr. Rogers' Neighborhood with that Brian identified as the celeste instrument. Very beautiful and clean, a pure kind of sound, innocent. Third one's from Psycho, how fear and terror can also be very high-pitched, like the violin screeching. What a really genius movie score that is. So yeah, tell us a little bit about, did we evolve to hear this? Like, I think pretty much if someone hears a scream, they're not saying, oh, that's good. So
Yeah, definitely. So there is a deeper region in your brain called amygdala, which we share with animals as well, and it is responsible for your fight or flight responses. And that region really monitors the sounds around you. And whenever you hear something striking, like say a scream or a baby crying, that region really activates and alerts you to the sounds. But if it's a happy sound, for instance, which doesn't need any kind of alerting, it is further sent to the auditory cortex that we were looking at earlier, and there then it's further processed to make decisions as to what to do with the sound.
I was reading somewhere where they said back in the day, sound was probably very important and tied to survival. That if you heard a sound, either that meant something was food for you, or you were about to become food for something else. So, and I wonder with the ha ha sound, how you said it's laughing, like it goes to your cortex where the intellectual processes happen. That's also probably tied to your body, right? Because when you're happy, the brain probably also, that's probably part of hearing or interpreting sounds too, right? Because amygdala what it shoots, what is it, adrenaline into your system, that it's fight or flight. Is that true?
Exactly, it generates those responses.
Amazing. Well, again, I'm so in awe of the human brain, because the whole hearing something and how that becomes meaning is something that's still very, I think you said it's still a lot of unknowns, right? How it exactly works, and it's just such a thing of wonder and mystery. And I think I feel that way about music too, because I don't know if we can talk about the evolution of Western music, definitely, and the piano is a good representation of this. The whole harmonic system notes is something called equal temperament, and that means what Western music and instrument, what they do with their instruments is they divided an octave, which is the same note to the note above it or below it. They divided it into 12 equal proportions. So that's why it's called equal temperament. But whereas in nature and also in non-Western music, that's not the case. There are notes between the notes, and Western music theorists call it microtones, semitones. And it's really interesting because theorists have looked at the whole of Western music, and they developed a system called counterpoint, where they look at just laws of nature where notes tend to move in certain ways and they sound better, and when you don't follow the rules in Western music, it sounds a little bit odd or off. They've given emotional descriptions to different intervals, whereas the bombastic, the proud theme for the Olympics were mostly perfect fourths and perfect fifths, which really they don't exist in nature. Whereas the jaws is the half step, or the screaming of Psycho, and then Mr. Rogers, the major third, or minor third, major key. But as a jazz musician, I think it's fascinating when the West Africans were brought over as slaves and could not play their own instruments. They had to adapt using Western European instruments, where this equal temperament system, which they were not used to. They didn't know about this. And the piano is like the perfect representation, right? But for them, when they played, to express their emotions, they needed notes between the notes, where I think this is where the blues, we call it the blues scale, but just the bluesiness of that kind of playing is trying to get to the notes between the notes. And I just think it has its analogy to what we study today with the brain. And just thank you so much for sharing your knowledge and your expertise with us. And I think before we go, let's do a closing activity in nod to the season. We're almost at Halloween, and I'm not as familiar with the music from this particular Snoopy show. I know Thanksgiving and Christmas, but I was very happy to find out about It's the Great Pumpkin, Charlie Brown. And so for fun, let's all participate in this experience of listening, using our ears, our cochleas, our auditory cortex, and interpreting in our brain which song is which. So I'm going to play these in random order, and based on what you hear, what song do you think I'm playing in which order? So I'm just going to play, I'll say each one as I play it. So here's the first one. Here's the second one. Okay. Next one. And last but not least, Facebook, YouTube family. Anybody want to hazard a guess what order that I play these songs in? Goodness, we got it right. Genghis Haas. Bravo. Bravo. Well, before we go, does it, Breathless? Okay, well, almost. First one was the Graveyard Theme. Second one was the Great Pumpkin Waltz. Third was Breathless. I was trying to make it obvious by gasping for air. And the last one was the iconic theme, Linus and Lucy. Thank you all for participating. And I want to welcome back Prachi to the screen. And if we have time for some question and answer, if you want to learn something more about hearing and listening, this is an opportunity I would not pass up. We have one of the world's brilliant scientists with us, and would love to discuss anything additional.
Let me see. Sorry, I have a question. I'm gonna just jump in here. We're getting some questions from the social media world as well. But Prachi, I have a question about sound and hearing as it relates to hearing loss. My father had tremendous hearing loss and actually had a cochlear implant. So at what point does a cochlear implant, what does it replace, and what does it do that the cochlea couldn't do any longer?
So this is not my area of expertise, but I'll try my best to explain. Overall, with age, what happens is those hair cells. Sorry, do you hear background noise?
Okay. I hear that. It means, I know what it means.
Yeah, so what happens really with age, those hair cells die, and so they can't convert the sound from the cochlear vibrations into the electrical signals that are supposed to be fed to the brain. And this really happens over the larger, like high frequency areas. That's why you kind of lose those high frequencies as you age. And what the implant does, I think, is to stimulate those parts whenever the high frequencies are playing, so that those electrical signals are generated.
Oh, so the hair is no longer, because I remember seeing a video about the dancing cochlea hair cell, how it actually moves and it stops moving, and so the cochlear implant replicates that.
I think so. Yeah, that's what really happens. But overall, like hearing loss are of so many different types. I'm just talking about one specific type of hearing loss. The research that I shared with you guys today, where male and a female were simultaneously talking and you could focus on one or the other speaker, that type of research is supposed to help people by stimulating regions of your brain directly to help amplify one of the speakers based on who you're trying to attend to. So those type of implants are also like going to be the future of hearing aids.
Wow. Amazing. Well, I did want to ask, what does a siren do to your brain?
That really activates your amygdala, I think.
Definitely, like that for particular frequencies probably will trigger the amygdala. Like
Yeah.
Well, I was curious about, like, Ryan's father. Was he able to articulate what he could now hear, and could he compare it to what he used to be able to hear? And
Yeah, that was always very interesting conversations, because he grew up being able to hear and slowly over time lost all of his hearing and was basically deaf for 20, 25 years.
Oh, wow.
So when he got the implant, he remembered what things sounded like. He remembered what a bird sounded like. He remembered what a car horn sounded like, but he said they didn't sound like he remembers them sounding. They were different, like his, and when you think about how abstract sound really is, like he couldn't really articulate what the difference was. He could still tell that a bird chirping was a bird chirping, but it didn't sound like he remembered what birds chirping. So it was and he was a big music fan also, and spent a lot of time going actually to the company that had built his implant. He ended up doing a lot of research with them, going out to the facility, and they would do a lot of tests and research on him. And one of the things that he was very interested in is how, because music, he could never really hear music again in a musical way. He could hear voices, he could hear sounds, but music didn't sound musical to him, even with the implant. And one of the things that they were researching was how to develop the technology to actually hear music better. And I think to what you were saying, the polyphony, the number of frequencies that exist within a piece of music just made it probably overwhelmed the technology, so it couldn't differentiate enough, whereas a single voice maybe was easier. He did end up listening to more music, but it was primarily the thing that he gravitated towards, oddly enough, was things that were more rhythm and bass heavy. Things that, not anything that was as complex musically as like orchestral pieces or something where you have 50 different frequencies and timbres happening at the same time, but something with a steady bass rhythm and drums, he actually could hear and enjoyed that. But again, he wasn't able to necessarily describe the difference, which I always found was fascinating. And I would ask him questions all the time. Well, what does it sound like? And he couldn't really articulate what it sounded like.
I wonder if it's related to like when we record, like the whole analog versus digital, because digital recording is a digital representation of the natural sound wave. It's very close, but still there are those little, it's pieces versus a continuous sound wave. And I wonder if that's what a cochlear implant does to the sound, because it's a digitized version of your cochlea, the hair of your cochlea moving. I mean, that's fascinating. Wow.
Yeah.
Like the speech sound is limited to about 3,000 hertz, but human hearing goes all the way to 20,000 hertz. And those higher frequencies are super important for music perception. And like when you lose your hearing, if it's like if you lose everything, most things that are restorable is at the lower frequency ranges, because speech in general is more important to us. So you kind of lose those high frequencies anyway. And that really makes everything sound a little robotic. So you lose those finer perceptions.
Amazing. Okay.
Let's see. Got one more good question here.
Could insight from auditory neurology eventually provide information that is useful in musical performance, improvisation, or composition? Thank you so much for asking that. That gives me an opportunity to share another research of ours. Like how language is super structured. For example, if you talk about English language, the sound ba following a, ba, a happens like very frequently as opposed to b and c. So language is like super structured, and same is the case with music as well. Certain notes happen more frequently after certain other notes. So there is some structure there. And whenever you miss out on that structure, even if you have no idea about music theory, your brain will go, aha, something's wrong with that piece. So you do, like, composers use these things because there is some sort of like statistical information there, where if you like order the notes in a certain way, it will sound more consonant to you.
That's so cool. And you can see it reflected in the brain
activity. Yeah, exactly.
Amazing. And I think musicians, we probably do that in an instinctive way when we write music, because if it was always the way you expected it to be, it would probably be a little boring or uninteresting after a while. So it's like, there's that element of surprise and anticipation. And cool. That's a great question, Jonathan. Thank you. Any more? Is it time? Is it that time?
I think it is that time. I'm sure a couple more questions will come through, and we can always follow up on in our social media platforms. But I want to extend a huge thank you to you, Helen, for your continued partnership on this, and to
Thank you.
Prachi Patel from the Zuckerman Institute. This was, they're all amazing, and this is amazing. And for me personally, with my dad's connection with the cochlear implant, I was so fascinated with everything that you guys were talking about. So I really want to extend a big thank you to you both. And from the Zuckerman, there's a whole team of people that help make these things happen. Lisa Din and Alyssa Mayer, and of course Paula Croxon, who kind of got this all up and running. So thank you guys all very much for joining us. We do have our next session we have on the calendar for November 24th. And this will undoubtedly be another interesting. Have you guys started talking about it yet, Helen? Do you kind of have any insight as to where you're going to be going for the next one?
It's going to be within the world of memory, and I thought in the context of tradition and Thanksgiving, family history, memory, I think that's going to be a really also exciting, rich topic to delve into.
Very cool. And Helen, do you have any other performances coming up soon that we should be aware of?
Not right now. I'm doing something this Friday with a bassist friend at Hochstein's, I think, bass shop. It's somewhere in Long Island. They're doing live stream performances, but I don't have any of the info handy. I'm so bad. I'm sorry. You can check my website or social media. Always have the information there. But thank you for asking.
Yeah, for sure. And so we're going to finish up, folks, but thank you so much for joining us. If you would like to make a contribution to the National Jazz Museum in Harlem, you can do that by visiting our website, or you can text the word jazz to 41444, and that donation will go directly towards our ongoing public programming that we do at the museum. We put a real emphasis on keeping musicians working throughout the pandemic, and the money that you contribute directly goes towards that. So thank you all for joining us. Hope you have a wonderful afternoon. This video will be archived on both the National Jazz Museum in Harlem Facebook page as well as our YouTube channel. So feel free to share it with folks that you maybe have missed it, or you can always come back and check it out again in the future. So thank you all very much for joining us. Have a great rest of your day. Thank you.